Good morning, everyone. Design of reinforced concrete பார்க்க போறோம். What is reinforcement? Reinforcement is something that is inserted or embedded in order to increase the strength. That is for strengthening purpose. Okay. What is M and 20 stand for? Mix.
M stands for mix, ma'am.
Mix
20
design of
stands for
M20.
20 stands for strength.
Characteristic compressive strength. Of 20 Newton per mm square. Okay, what is this characteristics? That is when we cast 100 cubes, 95% of the cubes will be of 20 Newton per mm square strength. Okay, there can be a deviation of 5%. That is characteristic compressive strength. Then tensile strength of concrete is 1/10 of compressive strength. That is 1/10 of 20 equal to 2 Newton per mm square. Therefore, compressive strength is greater than tensile strength. Therefore, concrete is a compressive member. Take a beam. This is neutral axis. Say M20 grade of concrete. Okay. This is the depth of the beam denoted as D. Okay. Neutral axis is taken as layer 1. Okay. Then consider layer 2, 3 and 4. Same way in the bottom. 5, 6, 7. Okay. When this beam is loaded, say W. Okay. We know normally a beam will deflect for its self weight. Now when it is loaded, there will be a bending. Take length as 1 meter. Now the beam deflects in sagging. Okay. Now the load is applied and checked for deflection. Take a tabular column, layer, difference in length. Then we have to calculate strain. You know the formula of a strain, difference in length to the original length. This is del, okay, del L by L. Then we have to calculate the stress. The formula for stress is Young's modulus into strain, Newton per mm square. The unit is, and for the strain there is no unit. Okay. See, the neutral axis will remain the same. There won't be any stress or strain. So the difference in length is 0. So the strain is also 0 by 1 meter. The stress is also 0. Layer 2, take, there is a difference, there is a compression of 1 mm. Okay. So minus 1 mm. Then minus 1 divided by 1000. That is 1 meter equal to 1000 mm. So minus 1 into 10 power minus 3. Take Young's modulus as 1. Then 1 and 2 minus 1 into 10 power minus 3. The answer will be the same. Minus 1 into 10 power minus 3. Similarly for third layer, take it as minus 3 mm. Okay, it is compressed for 3 mm. Then what will come? Minus 3 into 10 power minus 3. Here minus 3 into 10 power minus 3. Layer 4, take it as 5 mm. So minus 5 into 10 power minus 3. Layer 5, here it is elongated. So it's a 1 mm elongation. So plus 1 mm. Therefore it is 1 into 10 power minus 3. Layer 6 plus 3 into 10 power minus 3. Layer 7, take it as 5 mm. Then it's 5 into 10 power minus 3. So what can you see from this? The stress is same but in opposite direction. They are produced equally in layers in opposite nature from neutral axis. We know for M20 the compressive stress is 20 Newton per 20 Newton per mm square, and the tensile stress is 2 Newton per mm square. For the same beam, compression zone is 20 Newton per mm square, and the tensile strength is 2 Newton per mm square. Okay. For load W1, okay, if stress is 1 Newton per mm square, it is strong in both compression and tension zone, because in compression the strength is 20, tension it is 2 Newton per mm square. If the load is increased now to W2, then the stress is say 1.9 Newton per mm square. The same thing, it is strong in both compression and tension. Then again the load is increased, say 2.1 Newton per mm square. Here it is strong in compression zone. But it fails or unsafe in tension zone. So in order to increase the strength in tension zone, we are embedding or inserting a new material, that is the steel is reinforced in the concrete. Okay, the reinforcement is made in steel zone. Okay, why we choose steel? Why the material is steel? You can ask me. There are aluminum, cast iron, etc. There are some few conditions. Okay, the first one is Young's modulus of steel is greater than Young's modulus of concrete. You know the Young's modulus of steel is 2 into 10 power 5 Newton per mm square. There is a formula for Young's modulus of concrete. It's as per IS 456. It is 5000 root FCK. Okay. If the grade of concrete is M20, 5000. Take it as 25 for the easy calculation. Then you will get 5 into 2, 25,000. Sorry, 5,000 into 5, it's 25,000. Okay. Then coefficient of thermal expansion of concrete and steel is approximately equal. Okay, the value of concrete is 1.1 into 5, 10 power minus 5, and for steel it is 1.2 into 10 power minus 5. If the thermal coefficient of thermal expansion is not equal, there will be a thermal stress created. Okay, so we have to design for a expansion joint, and this will lead to deterioration too. and there we have to design for thermal expansion, thermal stress, sorry. The design for thermal stress is a big concept, okay. Then third point, we have to check for ductility too. In case of cast iron, it is so brittle. The percentage of elongation of steel is greater than the cast iron. For steel, it is 23%. Okay. For cast iron, it's just 5%. So you can know how the elongation for steel is greater than the cast iron. And we have to check for weldability. Then bendability. In case of, we take it for the next floor level. There is a welding, okay. In case of steel, it is easy to weld. Then bendability, we do crank the rod in beams, crank, okay. And in beam column joints, also in column footing joints. Also, there should be a bond between the concrete and the material. So according to these conditions, Young's modulus, coefficient of thermal expansion, ductility, weldability, bendability, bond, the material is chosen as steel. Okay, to satisfy the stress, the material has to satisfy quantity, quality, and distribution. Okay. Quantity is according to the magnitude of stress. Quality is nature of the steel. It should be pure. Distribution is direction, how the reinforcement made, or point of application. Okay. Take a simply supported beam. And it is loaded AW. there will be a shear force and bending moment. Okay, as per IS 456 2000, the code says design for flexure. Flexure is nothing but bending. Okay, we have to design it for flexure. This is cantilever. I already said you, for a simply supported beam, this a bending will be of sagging type. For the cantilever, it will be of hogging nature. So this is the compression zone and this will be the tension zone. For a cantilever, this is the tension zone, the compression zone. Okay, sagging nature. I'm saying it for simply supported. Here it will be bending compression. At the bottom there is a tension. Okay, bending tension. So we know the concrete is weak in tension. So we have to provide the rod in the tension zone. Where have to provide it? When there is a tension here, a crack will be developed in this direction. So in order to arrest this crack, the rod is placed in the tensile zone. Okay. Now the tensile stress is taken by the rod. The position of the rod should be parallel to the direction of stress. Can you see it? It is in this direction. The stress is in this direction and it is parallel, okay, and perpendicular to the crack. These are important questions. Okay. Parallel and perpendicular. That is parallel to the direction of stress, perpendicular to the crack.